Welcome. So in this video, we'll be answering this question right here. It says two fair dice are thrown simultaneously. Let S be the event, the same two numbers being thrown, and let E be the event of two even numbers being thrown. Of the 36 possible outcomes, the number in which two different even numbers are thrown is 6. This information is shown on the Venn diagram below. Part A, on the Venn diagram above, write in the appropriate place the number of possible outcomes in which the two numbers are, then it gives us a whole bunch of things that we need to consider. The same, okay. The first thing that I want to do is draw myself a table just to kind of get my bearings a bit. So I'm throwing two fair dice. So that means I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, let's get a color out. What we're told here is that the number in which two different even numbers are thrown is 6. So let's just consider that for a moment. Two different even numbers. So we don't include 2 and 2 because they're both the same even numbers, but 2 and 4 and 2 and 6. And then we could have 4 and 2 and 4 and 6. We could have 6 and 2 and 6 and 4. So as you can see, 1, 2, 3, 4, 5, 6, that's where that number has come from. If I now want to figure out this thing right here, remember E is just two even numbers being thrown. So we're going to consider the same two even numbers. So let's just get another color out here. Let's get pink. So that would be 2 and 2. That would be 4 and 4. And that would be 6 and 6. So obviously the number here is going to be 3 because I have 1, 2, 3 of those. Altogether, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of two even numbers being thrown. 3 plus 6 is 9. Checks out. Okay, the next thing that we're going to do is we're going to fill out this section here. Remember, S is the same two numbers being thrown. So that would mean 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. So that means 1, 2, 3 of those are the same number, but they're not even numbers, because remember, that's this intersection point right here. So 3 goes there. Now, if I have 3 plus 3, that's 6. 6 plus 6 is 12. If I have a total of 36, that means 24 is going to go out here. Okay, that all looks pretty good. And hopefully you can see how this table helped us out here. Let's see if we can now answer these. So this says the number of possible outcomes in which the two numbers thrown are the same and both even. So the same and both even. Okay, so if I threw two numbers that are the same and both even, that's this 3 right here, because that's like 2 and 2 or 4 and 4 or 6 or 6. So that's going to be 3. The same but not both even. So they're the same but they're not both even. That's going to be 1 and 1, 3 and 3, 5 and 5. They're the same, but they're not both even. There's a lot of language here, kind of like interpreting the question. Neither the same nor both even. That's going to be 24. Okay, so hopefully that made sense, and hopefully it shows you the importance of doing this table here and just reading it carefully. I was kind of getting lost in all those words. Okay, here. Let's see if we can answer these, shall we? What is the probability that the two numbers thrown are the same? Well, if the two are the same, remember S stood for the same two numbers being thrown. So it's going to be 3 plus 3. So it's going to be 3 plus 3, and it's all over 36. So it's going to be 6 on 36. Now, when you're doing these things, you always want to simplify. So that's going to be 1 on 6. Remember, let's keep on going. So both even. Okay, so if they're both even here, let's come up. That's going to be 3 plus 6 for my E event here, 3 plus 6. 3 plus 6 over 36, which is going to be 9 on 36. And remember, we always want to simplify, so it's going to be 1 on 4. The next, the same or both even. So this means we're going to be including everything. So this is the same as union. So if I was to write this, this is the same as S, the union of E. That's the same. That looks like Sue, but that's not what I meant to say. So it's everything here. So it's 3 plus 3 plus 6. So it's going to be 3 plus 6 over 36, which is going to be 12 on 36, which is going to be equal to 1 on 12. Perfect. Let's just highlight all our answers there so we don't get lost. So it was 1 on 6, 1 on 4, and 1 on 12. Oops, sorry, I got that one wrong. 12 on 36, that's 1 on 3. Not, what was I doing? That's 1 on 3. Brain fade. Alright, there, 1 on 3. So 1 on 6, 1 on 4, and 1 on 3. Perfect. Let's keep on going. Next. So we're finding here the probability of S intersection of everything not in E. So let's come up here and just look at this for a second. So intersection of S, so here's S, and everything not in E. So I know that's just going to be this 3 here, because that's where they would intersect. So it's going to be 3 on 36, which is 1 on 12. Now let's keep on going. So the next one that we have here is the probability of S, the union of E, complement. So everything outside these two, which is just going to be 24. So it's going to be 24 on 36, which is going to be 2 on 3. Let's highlight those answers. And let's keep on going. Okay, in a second experiment, 2 fair dice are thrown. The event S is again the event of the same 2 numbers being thrown, but the second event, this time T, is the event that the 2 numbers thrown add to give 10. Oh boy. A probability table or Karnoff map has been partially completed for the second experiment. We're going to have to figure out the shaded boxes here. Okay, so let's get out a pen and let's see how we go here. Alright, so the first thing that we can recognize that we can fill in is here. If this is 1 on 36 and this is 3 on 36, this has to be 2 on 36. And remember, always simplify if you can. That's going to be 1 on 18. Okay, what else can we figure out here? Well, I know what S is going to be here. So S was, if I remind myself, S is the event of the same 2 numbers being thrown. So S is the same 2 numbers being thrown. And if we come up here to our table here, the event of the same 2 numbers being thrown is 1, 2, 3, 4, 5, 6. So it's going to be 6 on 36, which is 1 on 6. 6 on 36, which is 1 on 6. And that means we can fill on this one. If this is 1 and this is 6, this is going to have to be 5 on 36. Because 1 plus 5 is 6. And 5 on 36 can't be simplified. If this is 1 and this is 1 on 6, this has to be 5 on 6, because 1 plus 6 is 6 and 6 over 6 is 1. So that means if I was to go backwards, this is going to be 30 on 36, because 6 6s are 36, 6 5s are 30. Then I could come here and I could say if this is 2 on 36 and this is 30 on 36, this is going to be 28 on 36, and that's going to be 7 on 9. And now I could come here and I could say if I have 5 and 28, if I plus those together, I'll get 33 on 36, and that means that that can simplify down into 11 on 12. Perfect, and that's everything done there. So we've completed the Karnoff map. Now we need to find the probability of T intersection of S complement. So what was it? T, S complement is 1 on 18. So I'm just looking T, I'm looking S complement, 1 on 18. 1 on 18. Now the next is a union one. So whenever you got union, you can use your addition rule to help us out here. So what I'm going to do is this. I'm going to say the probability of S, the union of the complement of T, is going to be equal to the probability of S plus the probability of the complement of T minus the probability of S intersection the complement of T. Let's now fill in what we need to find here. The probability of S will be 6 on 36, because it's just that, 6 on 36. The probability of the complement of T, the complement of t will be 11 on 12, or 33 on 36. Wait, that was the complement, wasn't it? Yeah, 33 on 36. And then where they intersect, so S intersection of t complement, so S was 5 on 36. Oops, sorry. S, yeah, 5 on 36 minus 5 on 36. 6 minus 5 is 1, so it's going to end up being 34 on 36. And 34 on 36 is the same as 17 on 18. Perfect. Perfect. So just using that addition rule to go through it there, let's just highlight those answers. Whoops. Okay, next. Explain whether or not S and T are independent. Show working to support your answer. Okay, so what does it mean for things to be independent? So I would begin by saying, you know, if independent, the probability of S, the intersection of T, needs to be equal to the probability of S multiplied the probability of T. That's what we know by definition. For something to be independent, S intersection of T has to be the probability of S times the probability of T. Now I know everything here. I know S intersection of T. So S intersection of T will be 1 on 36. The probability of S will be 1 on 6. And the probability of T will be 1 on 12. Well, 1 on 36 is not equal to 6 12s are 72. 1 on 72. These are not equal. So you would say S and T are, are not independent. And that would be our answer. Independent events. S and T are not independent events. And we've shown our reasoning there through our working. Perfect. And we're all done. Hopefully you found this useful in going through these questions. This question might be a bit tricky for some of us, but as long as you followed along, you should be all good. Hopefully this was helpful, and I'll see you in the next one.